Bismillahirrahmanirrahim. Assalamu alaikum. I welcome you all to the lecture number 8 for the course of Data and Computer Communication. My name is Engineer Jaffar and I'm an instructor for this course. So let's start with the recapitulation of the previous lecture. In the last lecture, we have discussed about digital data to digital signals conversion. That what is the motivation and reason behind this phenomena where we convert digital data into digital signals. After that, we learned about several techniques that are involved for conversion of this digital data into digital signals, and these techniques are commonly known as line coding techniques. We have covered about 7 to 8 or 9 different techniques in which involved unipolar, bipolar, polar, Manchester, and their further classes. That what classes are there for these conversions. So, moving swiftly on today's lecture, today we will be starting our discussion for this another layer or layer 2 of OSI reference model. The layer is known as data link layer, and we will revisit quickly the review of this data link layer. We will recall that what data link layer will be providing, which services they will be providing, and there is a subclass of data link layer. You know that data link layer has two classes. The first one is LLC, that is logical link control, and the second one is MAC or MAC, that is medium access control. And in MAC we will further discuss the random access control methodology or technique that is used in any communication network. So let's talk about broadcast media or a shared media. When you have a shared medium, so it is commonly used by all of the devices that are connected to that media. So this is a single channel which is shared, and in this type of networking topology, there is a highly chance of collision. Now, what is collision? Collision is a phenomena which is occurred when two or more devices tries or attempts transmission on that same channel or single shared channel or medium. So there is a phenomena of collisions. It occurs if the node or receiver or any device receives two or more signals at the same time. So it is basically a collision on the receiving end side. So this is known as collision, and this occurs when there is a shared medium or a single channel that is used for different devices communication. And this occurs in mostly the broadcast scenarios. When we are talking about unicast or multicast, specifically unicast, there is no collision takes place because there is a single channel, and this single channel is always dedicated to two devices. Between two devices there is a single path, but this is restricted only for these two devices. So let's go further. Now, what is MAC protocol? Let's talk about the two things. The first one is LLC. If you recall that data link layer was divided into two subcategories or two subclasses. The first one was LLC, that was logical link control, and the second one was MAC. So the main phenomena behind this collision is the MAC control. Now, what is a MAC? MAC, or commonly termed as medium access control, these are protocols which which are there to decide that how this channel is divided, so that every user or every device can have their certain amount of time to use that physical channel or physical cable or any physical link. You do not want your data to get lost because of the collision, so you always want to have the control on a different certain level so that your data is not lost. So to avoid collisions, you have certain amount of protocols. The first one is known as random access protocols, the second one is control access protocols, and third one is channelization protocols. We will start our discussion of the MAC layers from the random access protocols, and specifically in today's class we will study about Aloha. in the later sections or lectures of the course series, we will also discuss all of these remaining protocols. But in today's class, we will be starting that random access, that the first class of random access protocols. So let's talk about the random access protocols. So in random access protocols, there is no station that is superior to another station. So means all of the stations, the first assumption that you have to keep in mind, these are the assumptions, and the first assumption that you have to keep in mind while going into the random access technique, that is that you have all of these devices for you are equal. There is no superiority of any device on another device. So all of the devices have the same probability of sending the or transmitting the data towards their respective destinations. So there is no seniority, or you can say there is no superiority of any device on other devices. So the first one is the assumption, and the second assumption is that there is no control of one channel or one device on another device. It means that no device can control the channel from other device. So if let's say there are three users, user A, user B, user C, so all of these devices have the same permissions, or you can say the same control of on the channel. They do not have the control on each other. So it does not involve that A can control the utilization of the channel by B or C. So using these two assumptions are there for the random access protocols. So the first technique that is known as Aloha, that was developed at the University of Hawaii in the early 1970s. Aloha was the first technique that was evolved, and keeping in mind the random access technique. The medium is shared in this Aloha. The medium is shared between all of the stations, and when a station sends data, another station may attempt to do the same at the same time. So there is a higher chance of collision, because this is a random process, and random process involves probability, and there is a high chance that when the one transmitter is transmitting their data, there is a high chance that other transmitter also starts transmitting their data as well. So the data from the two stations may collide and become garbled or garbage. So to avoid this kind of thing, we will have to look into certain amount of presumptions as well. So to justify our signal, so that we know that if our data has been received properly or not, or it has not been corrupted, or it has not been collided in the path towards their destination. So we use a term known as acknowledgement. So it is based, this Aloha was based on the acknowledgement. The receiver will have to send the acknowledgement back to the transmitter, so that the transmitter know that my data has been reached to its destination properly without even getting corrupted. So the time transmission time is known as the time required from a data to reach its destination from its respective source. So that is known as transmission time, and it is generally equal to the ratio between the message, the length of the message, and the data rate. So if your message length is let's say your message is of 10 bytes, so and data rate it's 10 bytes per second, so it means that the transmission time will be 1 second. So this is the graphical representation of Aloha. So you can see that there is station 1, there are 4 stations, station 1, station 2, station 3 and station 4, and these 4 stations are there to transmit their data towards their respective destination. So let's say at this point of time only station 1 is transmitting its data, so there is no collision at all. You can see that there is no collision at all. After some time, this station 3, after this time station 3 have started their transmission, and when this time was reached, because station 2 doesn't know that this was transmitting, this station 3 was transmitting, it started transmitting their data towards its destination. So you see that the collision has been started from this side where the data was transmitted by station 2. Similarly, station 1 starts transmitting data at this point of time. So there is this collision. This is the whole collision duration in which the data was collided. This bracket, you can see that from here to here, this is the collision bracket in which there was a certain collision amongst the data. Similarly, at this point of time, the result will be nothing, because all the receivers will be getting a garbage data, a garbled data, so they will discard it by not and will not send acknowledgement back to the receiver, the transmitter. So after certain amount of time, let's say this station 2 starting transmitting data, and after some point of time station 4 also started transmission data. So you can also see that the collision duration will be from this point to this point. So all this data will be lost and no acknowledgement will be sent back to the transmitter. And after that, some time, this station 3 started transmission, and there is no other transmission is going along from this point of time. So there will be no collision at all. So you can see that this is the collision and this is the collision. So this is also the Aloha, that is the operation of Aloha. So let's discuss about the operation or the working principle of this Aloha. So let's say K is the number of attempts, TP is the maximum propagation time, TFR is the average transmission time, and TB is the backoff time, which is equal to R cross TP or R cross TRF. And what is R? R is the random number, which is generally any value from 0 to 2k minus 1. So these are some assumptions that were laid by this company or this designers of these protocols who designed basically this Aloha. So let's say if this station, any station, let's say this station, there is a station, let's say station 1 has to transmit a frame, or it wants to send a frame. So it will start with the value of k equal to 0. This will be their first attempt. So this will be termed as 0, and it will send the frame, and it will wait for 2 into transmission this propagation time. Now what is propagation time? Let's say this is your transmitter and this is your receiver, and the time required for any of the data to reach from this point to this point is, let's say, 1 hour. So 1 hour here. So it will have to wait for 2 into that time. It means it will have to wait for 2 into 1 hour. That makes it 2 hours. So this station will have to wait for 2 hours, so that it will have the, because you know that if it will take 1 hour to send the data from the transmitter to receiver, so it will also take 1 hour from the receiver to bring the acknowledgement from the receiver towards the transmitter. So 1 hour plus 1 hour becomes 2 hours. So it will have to wait for 2 hours so that it can get their acknowledgement. If the acknowledgement is received, it means the transmission was successful and there was no collision involved. And if the transmission is the acknowledgement is not received, it will increase the attempt value from 0 to 1, and it will decide if the maximum value, the number of attempts is greater than or less than a maximum value. Let's say you have kept that there should be only 5 tries, 5 attempts to transmit any packet. So if the value of this attempt, the new value of attempt is greater than 1, it will follow this path. Or else, if it is beyond that value, let's say this is your 6th attempt to send the same transmission, same packet, it will discard or abort the transmission by saying you that your limit has been exceeded. I'm sorry, you are not longer eligible to send your data again. So this is a condition over here, and if you are less than, let's say this is your second attempt, or the value of k becomes 1, because 0 plus 1 becomes k is equal to 1, and if it is less than, this is not equal, it is not satisfied, so it will follow this path and it will choose r. And what is r? R is any random number. It will choose any random number from this range, that is 0 to 2k minus 1, and it will wait then tb. And what is tb? This is back of time. It will, because r is random, so this tb also becomes random. So every station will have to wait a random amount of time, and it will respond back to the same frame, and it will this loop will be carrying on until and unless you reach here or here. This process will be stopped unless you reach at this point of this point or at this point. Either you will be successful or your transmission will be aborted. So you until and unless you are some point here or here, this thing will be keep going on. So let's talk about the vulnerable time. So vulnerable time is, as I've told you, that it is at least the twice time. The VT is basically the twice of the transmission time. It means that let's say this is your transmitter. Let's say this is A, and this is the receiver. Let's say B. So from here to here it take 1 hour. So let's consider that if your a collision has been occurred over here at this stage, when the data was when data reached over here, P started transmitting and their data collided at this point. So this collision information will be sent back to, it will take same amount of time and it will reach over here. So this time will be at least twice of, it should be at least twice of the transmission time, because let's say that here it was 55 minutes. So 55 this way and 55 this way, so it makes it 1 hour and 40 minutes. So you have to take care of that as well, because you do not want, because it is also possible that just before a second there is a collision. So it will take 59 minutes again to retransmit that information, to have to wait for the acknowledgement packet. So this is your vulnerable time. And now what is throughput? Throughput is given by any amount of data that you transmitted successfully. Throughput is a, you can say, let's say if you have transmitted 100 packets, and out of that 100 packets your 90 packet has been delivered properly, so your throughput will be 90. Throughput is basically, I've already discussed the parameters of any network in the lecture number 1 and 2 in detail, so you can revisit lecture 1 and 2 so that you have a clear idea about the throughput. The formula for throughput of Aloha is given by G into exponential minus 2g, where g is the number of stations. As the number of station increases, there is a high chance of collisions, so that the throughput is going down. So g is the number of stations who want to transmit, and to find the maximum efficiency, we have to take the derivative. If you apply the final value theorem FVT, you will get the maximum and minimum values of this throughput. And if you take the derivative of this equation with respect to g and you give it to 0, you can get the maximum efficiency, which in terms of Aloha turns out to be 18.4 at g is equal to 1 by 2. So when g is half, the value of g is 1 by 2, you get the maximum efficiency of 18.4, which is not that much of good quality, because it is showing you that if you are transmitting 100 packets, out of that 100 packets only 18.4 or 19 packets or 18 packets will be transmitted. The rest of the packets will be discarded or garbage. So this is not a quite good performance of Aloha, but it was back in 1970s, it was a really good achievement at that point of time. So let's talk about a pure example of a pure Aloha. So this Aloha is commonly known as pure Aloha. There are two types of Aloha. The first one that we have just discussed, and the second one we will be discussing after this. So Aloha, that is a slotted Aloha. So this is pure Aloha. A slotted Aloha is you can say a modified version of the same Aloha. Pure Aloha network, let's say, transmits 200 bits per bit frames on a shared medium of 200 kbps. Now, what is the requirement so that we have to make this frame collision free? We want that this frame should be collision free. So the first thing is that you have to calculate the transmission time. So the message length is 200 bits and the transmission rate is 200 kbps. So your average frame time, that we already discussed the formula here. You can see that this was the formula transmission time, message length divided by data rate. So here the message length was 200 and data rate was 200 kbps. So your time turns out to be, average frame time turns out to be 1 millisecond. Now the vulnerable time is 2 cross 1 millisecond. 1 is from here, so it becomes 2 milliseconds. This means that there should be at least the gap of 2 milliseconds between the transmissions of any two stations. So this means that no station should send the later than 1 millisecond before this station and after this station. So there is a guard band of 1 millisecond before the transmission of this station, and the guard band of the same 1 millisecond after the transmission of this station. So no other station have to transmit their data from before 1 second before this transmission and after 1 second of this transmission. So to make it collision free, you have to follow these rules. Now unlike pure Aloha, slotted Aloha are some kind of modification, but we will discuss it that the performance and the efficiency of this slotted Aloha is also not that much of good quality, but it has outclassed the previous Aloha version. Because it used fixed time slots that was assigned to the users or the stations. So it means that one time slot means one transmission time, and the transmission time is given by the same. There was the assumptions that a transmission time is equal for everyone, and every station should start transmission as its slots begin. So no mid slots transmission will be allowed. So every station has to wait for its time slot, and in that time slot it will have to transmit the data. So let's say we have divided the time into slots: slot 1, slot 2, slot 3, slot 4, slot 5, slot 6. We can see that there is no collision over here, but at slot 2, station 2, at this point of time, station 2 started transmission because the slot 2 has started, and the same amount of time slot 2 station 3 has also started. So slot 2 is now being collided. Similarly, this slot 3 is also being collided, and slot 4, slot 5 and slot 6 is not collided, because in this kind of Aloha only the user that has that wants to send the data has to start the transmission at the instant that the slot starts. In between the slots there will be no transmissions. So we have basically reduced the collision, but this is also not a good in terms of if you can do the same homework of all of the things that we have discussed till now. If you do the same thing, you will see that the efficiency is basically improved. Efficiency is doubled, but this is also not that much of you can say breakthrough. At that point of time it was, but nowadays it is not. It means that if you transmit your data, let's say 100 packets you transmit, and out of that 100 packets only 37 packets now has been received on the receiving end. So this was not a good this is not a good throughput in nowadays the scenarios of nowadays, but it was a nice effort in the in that period of time. So this was the slotted Aloha. So this was all the recap that we have discussed in the previous lectures as well, and in today's class we have discussed about the slotted Aloha, specifically the MAC protocol. That we started our discussion with the data link layer, and after that we discussed about the different protocols that are used by a MAC layer, and after that we discussed specifically the random access protocols, and in random access protocols we discussed specifically of Aloha, that we found out that the efficiency of Aloha is basically 18.4, and that was in pure Aloha, and slotted Aloha it was 36.8, which is not that much of good quality. So in the coming lectures we will be following further more techniques that we will be seeing that has improved the throughput of this communication network. I hope that you have learned quite a lot in this lecture. If you have any questions regarding these topics, you can write it down and bring that question into the class. You also know that I really appreciate and will provide give you the bonus marks if you are asked any brilliant questions from these discussions, because you know that I believe in the more you ask, the more you learn. I'll see you in the class. Thank you very much. Allah Hafiz.